In this lecture, we're going to talk about variable amplitude loading. And really, with our project, we've been dealing with variable amplitude loading kind of throughout the semester. But I wanted to pull a few of these ideas together in one lecture. I want to talk about rainflow cycle counting again, not the details, but kind of the overall perspective of it. And I want to talk about some other ways that people have dealt with variable amplitude loading besides rainflow cycle counting, and then why rainflow cycle counting really is the best way to handle variable amplitude time histories. So we've talked about the stress life approach, the strain life approach, and the fracture mechanics approach to fatigue and fatigue crack propagation. And so far in those examples in the lectures, we've talked about constant amplitude loading. We mentioned at the beginning of the semester that constant amplitude loading, if we looked at our axle, it would be fully reversed and has an amplitude defined for a particular waveform. It has a range defined. Of course, the amplitude would be half of the range. We talk about mean stresses and all these different things, but basically we said when we tested at this constant amplitude, then we could create some sort of curve, either a stress life or strain life curve, or some kind of fracture mechanics type curve, where we would have maybe the log of whatever loading parameter, S or sigma or epsilon, and the log of the number of cycles or number of reversals to failure over here. And we can use this plot then to determine what our fatigue lives may be at places in between our data points by using an appropriate interpolation or best fit on our log-log type axes. Well, determining cycles and what constitutes an up and down in variable amplitude loading is sometimes kind of difficult. If we were to take a look at a variable amplitude loading history, we have sigma versus time, and whether or not we start at zero, we can say that we do. Kind of bounces around. We have some highs, we have some lows, and the time histories that we've looked at are fairly representative of what you might find in the automotive industry and even the aircraft industry and even other industries as well, even the railroad industry, even though the axle tends to go pretty much constant amplitude loading. You can hit bumps, you can have other things that cause all these wiggles in our time history. And so there are different ways to kind of look at this. In one way, you could say, well, I kind of see maybe some sort of cyclic loading here. Then we have all these little things. So maybe we have some little cycles and we have some big cycles. We'll talk about how to deal with that. We've already talked about Miner's rule a little bit, but we'll talk about that some more as well. So when people first approached this problem, going back before, say, 1960, there were different things that we can do to figure out what's going on with it. In general, we can come up with a sequence of things that we need to know to be able to do a life calculation on variable amplitude loading. Let's make a new slide. We'll make some notes. All right, so we'll kind of take each one of these and talk a little bit about them. So the first one I had listed was stress and strain calculations. So most of our damage parameters will depend significantly on the stress and the strain values. So it's going to be important to have good or reasonable stress and strain calculations. So on one end, you could be an analyst that uses basic machine design type formulas or mechanics of materials. Our basic stress analysis formulas and come up with a state of stress. And right now we haven't gotten into multi-axial fatigue at this point, but based on a load history or something, you can come up with a local stress history as a function of time. Or if you have a complicated state of stress or multi-axial state of stress, maybe you can find a principal stress history at a certain state over time. So there's ways to deal with that. Now, in more sophisticated or more complicated situations, you might use finite element analysis to determine your stresses and strains. In some cases, you may also have to use plasticity. And of course, you may end up needing to apply some fracture mechanics. You may also end up using measurements of strains. Okay. So I teach classes in all of these different topics. So I teach mechanics of materials, I teach applied finite element analysis, plasticity, theory of elasticity, fracture mechanics, and experimental stress analysis, which is really more aptly called experimental strain determination or analysis. So all these things kind of build in order to determine the things that go into our damage parameter, which is the second item on our list. So we've had discussions of some damage parameters already. We may not have called them damage parameters, but that's what they are. We have our strain life damage parameter. The strain amplitude, or the strain range divided by 2, is equal to sigma f prime over E times 2nf to the B plus epsilon f prime times 2nf to the C, where sigma f prime and epsilon f prime B and C are coefficients and exponents that are related to either the strength, the sigma f prime and B, or the ductility of the material, epsilon f prime or C. And in this case, we're looking at the number of reversals, which is 2 times the number of cycles to failure. Okay, so in order to apply this damage parameter, we need to know those material properties, but then we also need to know what kind of things go into them on the left-hand side, which in this case is an extensional strain type quantity. Other damage parameters may have shear strain in them. They could have normal strains and shearing strains, and we've seen modifications where we have stresses and mean stresses in these as well. So all these things are different damage parameters. Which damage parameter should you use? Well, that kind of depends on what material you're using, what experience you have with the damage parameter, and what maybe your industry standard is. So maybe in the automotive industry, a lot of people like to use the Smith-Watson-Topper damage parameter, and in so much you could probably call that an industry standard type damage parameter for that particular industry. Another industry may use something different. It also depends on what material you're using. So damage mechanisms at the macroscopic level in metals are different than the damage mechanisms at the macroscopic level in something like rubber. Rubber can build up heat internally that can affect the damage inside that piece of rubber. So you may have a rate-dependent parameter, a loading rate or a strain rate or stress rate dependent parameter, and maybe something to do with the amount of heat buildup and the degradation of the polymer chains inside that piece of rubber. Maybe something to do with a cross-linking density. So damage parameters just typically try to capture at some level the gross or the macroscopic physical mechanisms that may be important to causing damage in that material. They don't necessarily have to capture the exact mechanism. So we know that the damage in metals has to do with dislocations moving, and you can probably find a dislocation-based damage parameter. But the idea with the sigma f prime and the epsilon f prime, the B and the C, is that those are kind of wrapped up inside those kind of overall material constants. If we could look into the material and know the movement of every single atom, that might be great, but from a calculation and particularly from a design point of view, it's very hard to be able to work with that level of detail when you're trying to make a product. So let me write a few notes on this page about what I've just talked about, and then we can take a look at our damage accumulation technique. All right, so maybe just a couple words just to summarize. Could depend on the material, depends on the damage mechanism, at least in a gross or macroscopic sense, maybe standardized for certain industries, and you could put anything in it that you want, really, that makes sense. Strain range, shear strain range, a stress range, a shear stress range, mean stresses, strain rates or stress rates, or different things like that. So anything where you can come up with a way to calculate a number of cycles to failure based on some level of something is a damage parameter. All right, so now let's talk a little bit about damage accumulation. We've already introduced the idea of Miner's rule, or some people call it the Palmgren-Miner's rule, and that's known as linear damage accumulation. All right, well, what does that mean? So let's go back to our constant amplitude test for a moment. We have stress versus time, and we have a sine wave, say, from our rotating bending test, and this just keeps repeating until the thing finally breaks. And overall, we have a certain number of cycles to failure, this particular stress levels. So at sigma stress amplitude 1, we have a number of cycles to failure of NF1. At a different stress amplitude, we would get a different number of cycles to failure. And now, what do I mean by damage accumulation? Well, when the object or the specimen was beginning to be tested, it didn't have any obvious defects in it. Maybe you took your specimen and polished it to a mirror polish finish, and you got it in as pristine a shape and as good a shape as you could before you started doing your testing. And then at the end of the test, the thing finally broke. Now, in between, we have these dislocations, thickening and darkening. We have the metal fatigue process. So certainly damage accumulated over the length of that test. And the assumption that we're going to make right now, at least for linear damage accumulation, is that each cycle contributed exactly equally to the amount of damage per cycle. All right, so if we have 1,000 cycles, okay, then the damage added up to be 100%, or the damage is 1. So whatever our life is, whatever our number of cycles to failure is, that's the total damage we can have, 100%, and have more than 100% damage. So we say that that is a life of 1. That's the total. It's the total damage that it can take. Well, if we had 1,000 cycles, each of those cycles, if they contributed equally, contribute 1/1000th of the damage. So that if we take the number of cycles times the damage per cycle, we get 1 for our constant amplitude loading. So cycles to failure times the damage per cycle is equal to 1. And this would work for whatever stress amplitude we have and whatever number of cycles we had for that particular component. Now we know with our stress life diagram that we do have scatter. So some specimens may end up with a little bit more damage than 1. Some specimens may have broken before we get to a life of 1. All right, so for design purposes though, because of the scatter and fatigue data, some people in some industries will apply a safety factor on the damage. So for example, if we have a safety factor of 2, that means our component would be calculated to fail when it has a total damage of 0.5. That builds some conservatism into this calculation, and it helps to account for some of that scatter. Now, what's the right safety factor to use? Well, it depends on how safety critical that component is, and what are the other trade-offs, and how well do you know your test data where this came from. So if you're looking at an SN curve on the high cycle side and you have very little scatter in your data, maybe a safety factor of 2 is fine. Maybe you're on the low cycle side and you have a lot of scatter in a SN type curve, then you may want to use a larger safety factor and maybe use a quarter for the total damage before you say that that is used up, or something like that. So typically the safety factor is applied on this total damage or the life of the component, and not necessarily on the stresses that are calculated. If we have variable amplitude loading, then the way to incorporate an accumulation of damage would be taking a look at the cycles identified at different levels. And we talked about our Miner's rule example previously, where if we looked at maybe S or sigma versus time, maybe we could easily identify what I call a block cycle loading, where maybe we have 2 cycles at this stress level and we have 3 cycles at that stress level. We can easily identify them as such. Maybe that needs to go up there to get my 3rd cycle. But what we would do, the total damage per block then would be the damage per cycle at stress level 1. So let's make it clear that's an amplitude. Times the number of cycles at that stress amplitude plus the damage per cycle at the 2nd stress amplitude times the number of cycles that happen in this block. And if we multiply these out, then we would get the total damage per block. Okay, well, what goes in here for the damage per cycle? Well, we just talked about that. That would be 1 over the number of cycles to failure at stress amplitude 1, plus 3 times then 1 over the number of cycles to failure for stress amplitude 2. I'll abbreviate it this way. That's the damage per block. And the damage itself over here can be related to life. In the same way as we got the damage per cycle here. So the damage per cycle is 1 over the number of cycles to failure, or the life. Well, the life is then the reciprocal of the damage, so the life in blocks is equal to 1 over the damage per block. So you calculate this damage and you get 0.1 for the damage. Take the reciprocal of 0.1 and you would get 10 times or you get 10, that means that this can last 10 blocks of this block cycle loading before it would fail. Well, with variable amplitude loading, we can do the same sort of thing. We identify the cycles and we figure out the life at that level of stress or strain, calculate the damage, and then accumulate that linearly. All right, so there's my variable amplitude loading history. We identify the cycles. We determine the life for that particular stress amplitude of that identified cycle, or strain amplitude, or whatever it is that your damage parameter is dealing with. In this case, let's just say the stress amplitude. Determine the life per stress amplitude, and then determine the damage is 1 over that life, and then your total damage is equal to the summation of each individual damage. And so this is our damage accumulation, and this is our linear damage accumulation technique. And this is really standard in fatigue analysis. Almost everybody in every fatigue analysis program does linear damage accumulation. We think about it a little bit though. Does that really make sense? Does the first cycle do just as much damage as the last cycle when you've got a crack that's almost going to break the specimen? So from that way of thinking about it, maybe it doesn't. It kind of depends on if you're in the low cycle range or the high cycle range. It's probably more justifiable in the high cycle range than in the low cycle range of a material. But it could be a little iffy either way. So I'm going to talk a little bit about nonlinear damage accumulation, but I will say hardly anyone really uses nonlinear damage accumulation, and we'll talk about why that is. So let's talk about nonlinear damage accumulation. And if we want, it might make sense to think of damage in life as being plotted one versus the other. So over here we have 0% of the life used. Over here we have 100% of the life used, or a damage of 1. So this is a case where we are exactly at the 1 for the fracture, the breaking in half of a component that we're testing, whether it's a specimen or a component. And so with linear damage accumulation, what we're saying really is that we have a nice straight line relationship between damage and life. If we're halfway through the life of the component, we've done half the damage. We're 3/4 away, we've done 3/4 of the damage. Okay, so what might this look like if we have a relationship that was nonlinear? So I'll try to use a different color. Maybe this kind of looks something like this. You have maybe a lot or a little bit of damage in the beginning. It kind of has a region where it's kind of constant damage in life, a straight line relationship, and then maybe it kind of goes like this towards the end. And you can think of other schemes too. Maybe it goes the other way and kind of accelerates more damage as we get close to the end of the life, or different things like that. So in this case, one model for nonlinear damage accumulation is that the damage has another kind of material parameter in here that we need to fit. So N is like the current number of cycles. At some stress level. Capital N is the fatigue life at that stress level. And this fitting constant is some sort of parameter that maybe it is in between 0 and 1. So this damage fraction can change, and we could have more or less damage per cycle as a function of our life if we want. Now, Miner's rule is recovered when P is equal to 1. All right, so why don't people use linear damage accumulation routinely? Yeah. So that's the reason right there. There's another thing you have to do, and you have to figure out what that exponent is, or whatever scheme you're using to come up with a nonlinear damage accumulation. You need to figure out extra material parameters. And that's not necessarily easy to do. If you work in the lab, hardly any test is easy. Even something straightforward like a tension test, there's a ton of things that can go wrong. Good data is hard to get. One of my mentors at General Motors used to tell me that all the time. You know, good data is hard to get. And so coming up with this extra material constants, it can be a difficult thing to do. And so, like it or not, most people tend to use the linear damage accumulation. Of all the things that go into fatigue calculations, this damage accumulation, being linear or nonlinear, is probably one of the lesser ones to worry about. Probably more important or more items that would give you more scatter or uncertainty in your fatigue calculation than worrying about the damage accumulation, particularly at longer fatigue lives. All right, so that's kind of the bulk of what I want to say about damage accumulation. Now, the last part of this will focus on our cycle identification and counting. So we've talked about damage parameters, calculating the particular things that go into the damage parameter, stress analysis, maybe we're doing finite element analysis. So since we're dealing with time histories and variable amplitude time histories, we have to figure out what counts as a cycle and how do we identify that so that we can apply our damage accumulation, damage calculation technique. So I want to give some examples of things that people did before rainflow cycle counting, and some people still use these techniques today. And I want to do that through looking at a particular type of stress history. Okay, so suppose we have a stress history that has a lot of superimposed ups and downs on it. So not easy for me to sketch this, have it look halfway decent. But if this was an electromagnetic wave, you'd probably say there was a carrier wave on top of an overall wave. So by looking at this in time, you'd probably say, okay, there's an overall sinusoidal nature to this, but then there's also this higher frequency oscillation on top. And this is not an atypical type of loading pattern that you might have. Think of a sign in the wind, and there's a gust of wind, and the sign bends. Maybe I can make a sketch to kind of let you know what I'm talking about. Maybe there's a big sign that looks like this, and the wind is hitting this surface, and it's pushing this into the page. So as the gusts kind of come and go, there's an oscillation like this that's pushing that back and forth. At the same time, maybe there's some sort of natural frequency thing happening, or maybe the gusty wind is kind of ebbing and flowing, but on top of that is a lot of very fast back and forth. So sometimes you see these kind of whip back and forth and vibrate almost. So that higher frequency may cause this superimposed oscillation on top of this. So that's where all these little ups and downs, these little squiggles would come from. All right, so do we have one big cycle? Do we have a whole bunch of little cycles? Well, in truth, we actually have both. Okay, but there are different ways that people used to try to measure these things. One method is called a level crossing. For that, I think I'm going to move my little picture over here somewhere. Now, back in the 1950s and 40s and so forth, computational power wasn't very great, particularly if you were taking measurements. So you really had to use your computational and your storage resources very efficiently. So what level crossing does is we take this history and we band it. So what I mean by that is that there are certain levels that we can measure that go up and down. And the level crossing says, okay, I'm going to put a mark in my column every time that my load history exceeds a certain value. And there's a difference between what we call cumulative level crossings or just level crossing data. So let's see if we can kind of think of this as cumulative level crossings in this case. Okay, so down here at 0, let's draw our bands. Okay, so here's my 0, here's my +1, my +2 band, my +3 band, and there's all kinds of terminology. You can have 0 between bands and all this kind of thing. And maybe this might be my -1, my -2, and my -3 band. And what I'm doing is every time I end inside of a band, or every time I cross a band, I will make some sort of count. So here we have this one, so maybe it went up to level 2, and then it went down to level 1, and then it's going up here, and then when we get down here, maybe it comes down this way. And so in the end, when we count all of these things, I'm not going to count them all for this history, but we might have 57 times it reached level 3, 85 times it reached level 2, 115 times it reached this way, and maybe this is fairly symmetric, so maybe this is 118 times, 73 times, and I don't know, let's say 61 times that crossed that level. So in a way, this cumulative level crossing gives you a feel for what's going on in that time history. If you look at enough of these and you look at enough different time histories, when you see this level crossing data, you kind of get an idea of what that time history is going to look like. This one is primarily centered around 0, but it exceeds things that go a little bit higher. Now here's where the level crossing can get a little bit weird. If you use this time history may generate this level crossing, but if you were to try to take this data and create a time history, you may not get something that looks a whole lot like that one. So what you might do is you might say, well, it got up to here to 57 to 61 times, so maybe I have 57 big cycles, and then I have more here, 85 and 73. Let's take the average, maybe that's around 80. Maybe I have about 80 cycles that look like this. And then maybe I have 115 cycles that look like this. And then I do my miner's rule and calculate the damage and all that for this. Okay, well, that's not really what we have going on in that time history. And there are certain histories that can kind of fool this cumulative level crossing type analysis. Okay, so I'm not going to spend a whole lot of time on cycle identification methods that don't work in every single instance. A very good standard is the rainflow cycle counting standard. There is an ASTM standard for rainflow cycle counting, and that's basically what I teach. I don't necessarily teach it the way the standard explains it, but I try to teach it from an algorithmic perspective. And we've talked about that many times, so I'm not going to go into huge detail about what is involved in rainflow cycle counting in this lecture. But let me show you what we would get if we were to use rainflow cycle counting on this particular time history. If we think of rainflow cycle counting in, let me kind of maybe draw a box around this, I'll use the same chart. We think of rainflow cycle counting in terms of our hysteresis loops, as we've been doing. It's not necessary to draw the complete hysteresis loop, as we've seen, but it's a nice way to visualize what's going on. If we were to look at this, we would have some sort of history that does something like this. I may not have the exact numbers of cycles, of course, but we have this type of history here. So by using this technique, then we have not only identified the main overall cycle that's occurring, which would be by this large hysteresis loop, but we've identified all of these little smaller loops. We can identify the mean stresses that go with them, the strain ranges, the stress ranges as needed, and so forth. So we have all the information that we can get about each identified cycle, which corresponds to a closed hysteresis loop. So let's make a note on a page for that. And so briefly, I want to mention ASTM standard E1049, standard practices for cycle counting and fatigue analysis, and it basically goes in and talks about these different methods. So we go through, they talk about level crossings, peak counting, that's another way you can count peaks and valleys. So that would be a way to make a count at a particular band range. Here's the level crossings that they talked about. So there's counting on only the upside of each cycle in some cases. Um, if you have squiggles in the band, maybe those are not counted. So there's all kinds of things like that. But again, I would discourage anybody at this point in time from using range counting or level crossing type data. And then they get into rainflow cycle counting, and this is their algorithm for counting cycles. So all of this is basically what we have done in our algorithm, hopefully in a much more understandable way. All right, so we probably reiterated a lot of these things that we talked about when we talked about our project for the class, which is to come up with a fatigue calculator. But again, this is the right time to talk about variable amplitude loading. And from a practical perspective, you'll often see a lot more variable amplitude loading situations than you will constant amplitude loading. So it's a very important part of fatigue analysis of how to deal with variable amplitude loading histories. Okay, please do contact me if you have any questions, and I think that's enough for this particular lecture.